talk about who I am. So I'm the organizer of the Austin RISC-V group. We meet once a month here in Austin. I'm an organizer for a new thing that I started called Works with RISC-V, and this is an online community for the RISC-V ecosystem to help people find stuff. So we're going to turn currently the Austin Linux group meets twice a month. We're going to turn one of those into an online meetup in January. And that's going to be a Works with RISC-V online thing. I'm a RISC-V ambassador, as you can see from the slide, and my shirt. I'm an old, so I've been doing more than 30 years of stuff with non-x86 architectures. Yes, I do run an iRISC box at home. Yes, it is very loud, but I can also run Quake on it. I'm here to try and make the world of computers more interesting, sustainable, and less controlled by billionaires. So let's get started. Why RISC-V? RISC-V is a free and open standard instruction set architecture. This hasn't been done before. And what's kind of cool about this is we've had no-cost ISAs like Spark, but we haven't, and Open Power is also a no-cost ISA. But we never had one that is open and free like RISC-V is. This is also different in that this isn't tied to a product. Open Power is made by IBM. It's still IBM processors at the end of the day. ARM is a available ISA that is free, but like there's large licensing costs with it. You can't just license the ARM architecture unless you happen to be Apple. And we've done some incredibly great performance leaps in a very short period of time. Carl Thompson made a very good point that this is a bad analogy, but I'm going to make it anyways. In the same time that Intel has gone from the 8088 to the 8386, we've gone to the performance of nothing to a Pentium 4, which is cool. Now, part of that is because we're riding on Intel's coattails. Like, they solved a lot of major problems in the 80s and the 90s, and we're like, cool, we can just use that and do something cool and interesting with it. But that's where we are. And we are 64-bit clean the whole time, which is great. Anyone can make a processor, but not necessarily anyone can get it fabbed yet. I'm going to be doing a project with Works with RISC-V next year, where we're going to start with a low-cost FPGA and go through the entire process of going from, I downloaded System Verilog off of the web, let's turn it into a microcontroller, using as much of an open source toolchain as I can. I can't guarantee that's all going to be open yet because I haven't done it. But that is my goal for something that we're going to try and do as a kind of like code along thing on YouTube and PeerTube next year. And we're just getting started. Being an advocate, I'm one of the true believers. And so we used to say that like RISC-V is the architecture of the next 50 years. And I very much believe in that, and that's what I want to do. And we're the folks that are going to try and enable zettascale computing. And if you don't know what that is, next door is Texas Advanced Computing Center. That's all HPC. They're currently doing what's called exascale computing. Zettascale computing is 10 billion floating point operations in 1 second. It is insanely fast. But it's the sort of stuff that we need in order to accurately predict the weather. So how do you RISC-V? What's cool is there is readily available hardware. For Linux and BSD, you can buy stuff like the Pine 64 Star Pro 64, the Milk 5 Jupiter, the Banana Pi F3, the Orange Pi RV2, the Hi-Fi Sci-Fi P550 Premier, and microcontrollers. ESP makes the C series of the ESP microcontrollers. It's the P series microcontrollers. Nordic Semiconductor makes a couple products that they don't like me talking about. And there's the Raspberry Pi 2350, which you can switch between ARM cores and RISC-V cores. I'm not going to spend a lot of time on microcontrollers because this is Texas Linux Fest. So I'm going to spend much more time talking about Linux-y things that you can do. In emulation, QEMU is there. It works. It's slow, but it works. Spike is another emulator that comes from the RISC-V organization for doing some of this stuff. There's a new one called RVVM, which is significantly faster than QEMU, but sadly doesn't support vector. We have Android, and in fact, Android has committed to RISC-V being a Tier 1 platform, which is pretty cool. We have the Sail RISC-V emulator, which is very not fast, but is very accurate. And then you have options from cloud. So you can actually go get RISC-V instances from Scaleway right now. I think they're like $5 to $10 a month. They're based on a Lychee Pi 4a. Come by the booth. I'll show you what they look like. There's another group called Cloud5, that I work with. They have a variety of hardware, and so if you just want a place to compile stuff, we'd love to talk to you and help you get started doing that. That's part of my job as a volunteer, because I don't get paid to do this. So the big thing that we need to talk about, and don't get scared about the really small text on the slide, it'll make sense in a minute, is profiles. So the flexibility of RISC-V is both, it's its superpower. Like a lot of people say, oh, fragmentation, it's a big problem. It's not. Austin and I like to joke that profiles are the lowest power state that you can have for running RISC-V. It's to try and make it as easy as possible. So because we're an open, actively developed ISA, it means things are going to change, and that's fine. Profiles are the answer to that. Every other architecture has this too. Intel has this. Everybody's like, oh, everything just works on x86-64, unless you try to boot Enterprise Linux 9 on older hardware. And then you get this message of like, this platform is unsupported and nothing works. And part of the reason for that is because they're using x86-64v3, and you only have x86-64v2 hardware. So these sorts of things exist on other platforms. Profiles are our way of trying to control that inside of RISC-V. The two major profiles that we have right now are, specifically for Linux-based stuff, is RVA20, which, if you're looking at GCC flags, is typically called RV64GC for legacy reasons. There was a 6-month fight. We lost. It is the oldest and the most compatible version, and it is comprised of these. So there's strings underneath. This is the actual architectural string. So what this is saying is RV for RISC-V, 64-bit version. I is your basic integer stuff, M is multiplication, A is atomic, F is floating point, D is double precision floating point, C is compressed instructions, and then there's a whole bunch of extensions to do things like make sure that you can actually fence between your instructions, rapidly move data back and forth, a few other odds and ends, and probably the most important one is like SV39 that says your memory bus must be at least 39 bits in width. RVA23 is the new hotness. It's what everybody wants us to have. The sad part is no one's shipping it yet. You can run it on QEMU, which is great, but not necessarily spectacular if you like want performance. This is the ISA string for RVA23. Like, that's how much has changed in 3 years. The two big additions, without having to go through all the little stuff, is like we've jumped from oh no, it's still 39 bits for memory, which is great. But the two major things are we have added vector, we have added hypervisor. And like those are kind of like the big deals. Vector, briefly, is how RISC-V, using the reduced instruction set computing principles, is doing a concept called single instruction, multiple data. So earlier on the slide, we talked about AVX are the big variants between the x86-64 architectures. Vector is how we're doing the same thing that AVX is doing, but unlike Intel, you can change the bit width, and by you, I mean the person making the silicon, to be 256-bit, 512-bit, 4096-bit, whatever you want. The instructions will be the same, so you don't have to go through and get new instructions if we decide, oh, hey, we want a bigger register. That's all supported automatically, which is fantastic. Let's talk about Linux distros. So RISC-V is tier 1 in Debian as of Trixie. It is built for RV64GC, so it's using the RVA20 profile. No big deal. Fedora has been working since Fedora 40 using RV64GC. This particular laptop is actually running on Fedora 41. I know Fedora 42 is out. It's sadly not supported for this particular piece of hardware, but we'll talk about that later. Starting with Fedora 44, there's going to be a parallel fork. So there's going to be one supporting RVA20 so that we can keep using the hardware that's already in the field. And there's going to be a new one for the upcoming hardware for RVA23, which is great. I applaud Fedora and the greater EL ecosystem for going down this route, as opposed to what Canonical chose to do, which is in 2 weeks, the new version of Ubuntu comes out and it won't work on any hardware. They have completely switched to RVA23, and they're only supporting RVA20 in the 24, excuse me, that is a typo, it should be 2404, my apologies, LTS for the next 2 years, and then after that, you're on your own, which is unfortunate. Arch works really well. A great guy by the name of Felix on Mars runs that project. It's one of the first new architectures that's being added upstream tier 1 to the Arch project, which is great. Interesting things are happening in Gen 2. We're actually trying to make, because of this RVA23, RVA20 thing, we're going to start trying to make hyper-optimized stage 3 tarballs of Gen 2 for the different boards that are out there so you can take advantage of all the capabilities with it, which is super neat. And shout out to our friends at OpenSUSE, they're doing stuff. And pretty much every single university in China has decided to fork either Ubuntu or Debian and make their own distribution with it. And so there's interesting stuff happening there, like they're making different optimization changes, things like that. I know this is Texas Linux Fest, but like I would be remiss if we didn't talk about our great friends at FreeBSD and NetBSD. You can even run Haiku on RISC-V if you are just longing for those BOS days. ROS is the robot operating system. And then the other big one, I put it on here, other is Yocto. So if you're not familiar with Yocto, Yocto is a distribution for making a distribution. It's a very big project that is run by the Linux Foundation. The Yocto project and RISC-V International made an announcement at the European Summit a few months ago that there's going to be tier 1 support for that for all of the major profiles. So if you're interested in bringing up something from nothing, you can start with Yocto. But then it's probably better to move to something like a Debian or an Ubuntu or a Fedora or something like that. So, important terminology thing. Because RISC-V is kind of cool and interesting, I refer to everything by the sock as opposed to the board. Because as you can see on this list, I've got 4 socks listed on this page and about 25 boards. It doesn't matter if it's on one board or another. There's minor differences between them. But for the most part, if something works on one board, it's going to work on another board. So I just categorize everything by the socks because that's where the upstream work is happening. That's where the enablement is occurring, and then we can kind of go from there. So starting at the top, you got the Star 5 JH7110. That's what this laptop is running. This is an in-order, no-vector, slowish processor. What do any of those words mean? Great question. There's 2 types of processors, in-order processors, out-of-order processors. In-order processors work the way that you think computers work, which is they get a list of instructions, they start at the top, they start executing the instruction one at a time until they get through all the instructions and get to the end. Out-of-order processing is how we get really fast computers, but it's also how we get Spectre and Meltdown. We are not vulnerable to Meltdown, which is fantastic. There are some issues with Spectre, and we've had a couple other interesting things with processors that are kind of hinted to on this slide. We'll get there. Out-of-order processors are faster. They are better. There's actually technology coming in RISC-V to address this problem once and for all, which is super cool. It's a technology called Cherry, C-H-E-R-I. And basically what this does is you put tags in the memory controller. So as the processor is going through and speculatively executing future instructions, when you get to a decision point and go, we're not going down that path any longer, you invalidate the tag, and all of that code ceases to function because it can no longer execute the memory, which means you don't have any of the memory leak things. It's very cool, but it requires massive changes throughout the entire operating system and every library. So we're getting there. There is stuff coming, but it's super neat. And the rumor is that it may actually be a requirement for Android phones that are running RISC-V, which is kind of awesome. Yes? Signed pointers is an interesting question, and I don't know the answer to that. There's probably someone looking at it, but I'm not aware of something at the moment. Also, by the way, if you have a question, feel free to raise your hand. Like, I would very much like this to be interactive rather than just me talking to y'all. Yes. Correct. Yes, they're all testing QEMU specifically. Yeah, so everybody's shipping QEMU images right now. Cool. So, Star 5 JH7110. The cool thing about the Star 5 JH7110, it is the best supported in the kernel. There's more details about that we'll get to in a minute. The next best one is probably this is pronounced space-time, I learned the other week. The space-time M1K1. So this is an in-order processor as well. It has vector, which is cool, but it is slow. You can get it through the Banana Pi BPI F3, the Milk 5 Jupiter, the Orange Pi RV2. The Orange Pi RV2 is like $60 on Amazon. It's really affordable and easy to get your hands on. These are great for things like you want to run a router, you want to build a small NAS. Great stuff for things like that. Then we have the SWIN EIC 7700. So this is an out-of-order processor. It doesn't have vector, but it's fast. The two shiny things at my booth are both EIC 7700s. So we have the Milk 5 Megres, which is one of the ones I have, the Sci-Fi P550 Premier, and you can also get the Pine 64 Star 64 Pro, which I did bring today, so if you're interested in that, it's very small. Great for like making compute clusters, not good if you want to run a GPU. We'll talk about GPUs in a moment. And then the last one is a processor with 3 names. This was originally a project by Alibaba, which was then spun out by T-Head, and is now called Zhuanti, and it's the TH1520. This is what is in the Lychee Pi 4a. It's also in the Beagle 5 Ahead. The reason it has a little ghost there is because there is a bug in this processor, which you might have heard about in the news, called ghostwrite. There was some debugging code, as best we can tell, that was left in the processor design, and it has an incomplete implementation of the vector implementation. So it's not vector 1.0, unlike the space-time processor. And it has a thing where you can use a undefined instruction that someone found through fuzzing, and you can write to any physical memory address. It's not good. It's not a big deal on most applications. The only place where it is going to be a problem is if you're in a shared user environment. So like if you're on like a shared web server and you foolishly left vector, pre-release version of vector turned on, then people can do terrible things with PHP code. But people can do terrible things with PHP code without that, so it doesn't really matter. But the reality is it's not a big deal for most people's implementations. Most people are running single user. It's not really a problem. It's not a remotely executable code flaw. It's just something that runs locally. But still, it's unfortunate. Like this is not sabotage. It's nothing like that. It was just an unfortunate side effect that was found in some research. So let's talk about some other things that are necessary to know for getting stuff up and running inside of this ecosystem, because the joke that I have been lovingly making for the last week is this is all about upcycling e-waste. So in order to do that, we need to talk about what certain things are. Every one of these boards that you can buy comes with what we call a BSP, which stands for a board support package. So the company that made the silicon made a version of Linux that comes with that board. And it's terrible, like guaranteed every time. It also comes with a firmware and a bootloader and a few other odds and ends, and those are usually okay, but the Linux distribution they put together is almost always bad. For example, the one that comes with this had a snapshot of Trixie when it was still in testing that only could get updates for 2.5 weeks before the keys expired, and there was no way to update the keys, but then if you then put the new keys on it and ran an update, it would completely break user space. Like, it's bad. So what we wind up doing is we have to use parts of this, though. Upstream's kernel support for these boards are very sparse, as I was saying before. JH7110 has the best upstream support, but does not have GPU support. Put a pin in that, we'll get back to it. The second best is the TH1520. So it's a current target for a lot of upstream work. A lot of that is being sponsored by Scaleway and SUSE, which is great. I don't understand why, but that's fine. And we're able to ride on the coattails of efforts from Texas Instruments, of all people, because it turns out the GPU that is in the TH1520 is also used by a TI part called the AM68. And they are paying Imagination Technologies, who makes the GPUs for all of these boards, to open source the drivers for that particular GPU configuration. We do not know if those open source drivers will work on RISC-V yet, but they're open, so there's a chance. And that's a great place to start. That also has the partial vector implementation, so there are some speedups that you can get there. So pretty much for every board that you're going to play with, what we're going to wind up using is the vendor kernel and the bootloader from the BSP, and then we can just replace the user space. Yes? Yes, you are 2 slides ahead of me. We'll get there, but yes, there is discussion around that. So basically what we're going to do is we're going to continue using, every SOC does have an open kernel tree. It is a vendor tree. There are weird patches in it. There are bugs. Frequently you're going to have to compile it to do things like make sure that the HIDRAW driver is enabled so you can change the color of the LEDs on your fans. Fun stuff like that. And they are stuck at older versions. The process of upstreaming is slow. It typically takes 2 to 5 years for a new processor to get upstreamed. And that is if there is a lot of community support doing it, because it's usually the community that pushes this forward. Which brings us to firmware and booting. So how do you turn these things on is complicated. In a perfect world, we would have UEFI. We'll get there. All of these boards support U-boot. If you have not heard of DOS U-boot, it is fantastic. It is lovely. It is derived from Linux code. Most of them have upstream support in U-boot for the boards. It's pretty straightforward. You take U-boot, you compile it with either OpenSBI or RUST-SBI. This is a RISC-V thing, which many people are like, oh no, it's a binary blob I'm putting in my kernel again. It's all open source. It doesn't matter. What the SBI does is it is the supervisor binary interface. RISC-V processors have 3 modes: machine mode, supervisor mode, and user mode. Linux uses all 3. So we boot in machine mode, and then we come up into supervisor mode. In order to make the system performant, we have the SBI to have a clean way of going between machine mode and supervisor mode. It provides one clean API that's all managed through eCalls. It's lovely. It means that there's a lot of board-specific stuff in there, and we don't care. The source code is all open. It's all BSD licensed. You have to build OpenSBI, and then you link it into U-boot. Everything just works. EDK2 is the open source root tree of UEFI. Unfortunately, EDK2 is BSD licensed. And the reason why I say unfortunately is because 25 years ago, all of the BIOS manufacturers forked that and haven't contributed any changes back since. So we have a lot of problems in EDK2. And there's a lot of low-hanging fruit here to solve. Like my favorite is you cannot plug in a keyboard newer than a 2009 Dell keyboard into something that is running EDK2. Because if it has a hub in it, EDK2 is just like, that's a hub, not a keyboard. I don't know what to do. This is super easy stuff to fix that no one has done. And again, the vendors have done this in their own trees, but they're not contributing any of it back. The issue is usually licensing. Like, normally, we had these sorts of problems in U-boot for a while. And someone was like, oh, this is easy. I'm just going to cut and paste code from the Linux kernel and put it in U-boot. They're both under kernel GPL2, and so that worked. EDK2 is under BSD. So probably what we should be doing is going and knocking on the doors of our lovely, wonderful friends in the BSD community, being like, hi, can we borrow your USB stack? Because we need one that works, and the one we have doesn't. And that just hasn't happened yet. But that's opportunities for folks to come into. The other thing that I will say is EDK2 is approximately 50 million lines of code. It is written by a committee of companies that mostly no longer exist, and it shows. It's a mess to get into, and it does far less than the Linux kernel does, but it's the thing that everybody wants. There are other alternatives. We're kind of trying to figure out how to move forward with some of them. Yes? Good to know. I will get notes from you from that later. Thank you. Okay, so now that we've gotten to the point where we have a bootloader, we have to talk about everyone's favorite thing, ACPI versus device tree. So this is the VI and Emacs of hardware. These are essentially 2 different technologies that solve the same problem. In order for us to boot a Linux kernel, we have to understand what the hardware is that we're running. And that has to be told to us by the hardware so that we have generic code that can run on everything. We also need to understand, like, remember those huge architectural strings? If people are implementing other extensions, we need to know what they are, and they need to come from somewhere. So it's either going to come from the ACPI tables or from device tree. There's a perception that ACPI is the best way to do this. It's not. And this is proven by, like, there's an entire patchwork to track ACPI alone in the Linux kernel. It is somewhere in the neighborhood of 1,000 commits a month just to keep up with what vendors are doing in the ACPI space. Yes? I'm sorry. Patchwork is a system that's running on kernel.org that watches the mailing list for specific parts of the kernel development tree and will create an entry for every patch that goes across and lets you track what its upstream process is, how many revisions there are, who's the owner for it, all that. It's a great way to keep track of what's going on inside of the various Linux trees before they go up into Linus's tree. Cool. So this was a huge problem in the ARM space, and so the software ecosystem decided to take the bull by the horns and then created the device tree standard as a way to do this. The issue with device tree is there's this view of too many sources, and part of that was because the device tree team had this vision that we would just have a DTB, which is a device tree binary, in firmware that everyone would use. But the reality is when people are building their own boards, they have NDAs as part of the IP blocks that they're putting in their socks, and so that they can't say that this is a Designware 3 PCI Express controller. They instead say that this is a SpaceMint PCI Express controller, and that goes into the U-boot stuff, and then when the Linux people find out, they change it to Designware 3 because that's the actual driver, and now we have two different device trees, and everyone gets confused. The way that I deal with this is you have a device tree that goes into U-boot, and when you build the kernel, or you build the FreeBSD kernel, you get a device tree that comes with that. Use the device tree that comes with your kernel. Don't worry about the one that's in the bootloader. Everybody's happy. We can move on. Question?
Yeah, I always find it difficult. How do you choose which device tree sources to pull from?
So you don't have to. Like, that's the great part. Whatever device trees are in the kernel you're building are the correct ones for that kernel. Full stop. It won't have to. So when you do a def config for your platform, it will turn on the device trees that it needs to compile. And you're pretty much good to go. So like I was building the kernel for the Megres the other day, and like 16 device trees came out of it. Ironically, one of them was a Sci-5 one, but that's because they pull in components from the same source file. But it was only like 15 files that came out, and only one of them is good for my Megres, so it's pretty straightforward. It's not like you're compiling 15,000 of them and taking up 3 gig of drive space. Cool? Okay. So this brings us to bootloaders and the tale of bootloaders, and the fact that bootloader is a very overloaded term. This is a sampling of how your computer turns on. You have the 0th stage bootloader. Yes, that is what it is called. That is on the chip and unchangeable. It is extremely tiny, and by extremely tiny, I usually mean it's under a couple hundred bytes. Its job is to go, there's a NAND device plugged into an interface over there, read code from it, execute. That loads your SPL, which is one of your first stage bootloaders. It's typically a component of U-boot. That then loads your supervisor binary interface. That then does your sock bring up, which gives you your U-boot, your OR boot, your Linux boot, all that fun stuff. And then sometimes you get an operating system loader on top of that, like your grubs or your EFI stub or EXT Linux. That big box that's labeled EDK2, all of that is replaced by EDK2, which is why it is so big and complicated. It takes 3 layers of it, and then you just access it through grub or EFI stub. Discrete GPUs add another layer of complication to this, which is people expect that they plug a monitor into their GPU, they turn the computer on, and they get a logo. That's hard. In U-boot specifically, they did not want to deal with anything that wasn't on the sock. So there's no way to do PCI Express discovery, find the code that is on the graphics card, execute it to initialize the graphics card to get a standardized frame buffer interface that can then be used by an EFI driver to put a logo on the screen or give you a menu. Like, EFI does all of this, U-boot does not. Other firmwares have different ways of doing it. It's a complication. Oh, and to make matters worse, the code that is on the card is x86-64. So you have to have an emulator that just in time converts that to RISC-V in order to be able to execute it. All of this that comes along to say is, the great things about standards is that they're all optional. Embrace chaos. If you have one takeaway from this talk, this is what I want you to have from it. in all seriousness, like there's a lot going on and it is complicated, and I don't want to pretend that this is, I can go download an Ubuntu image, plug it in, and go. Sometimes you can, but frequently it is an SD card image, and you also have to know which kind of SD card to use, because SanDisk SD cards work well, Samsung SD cards don't. The reasons for this are a 20-minute talk. A lot of that we'll glaze over for now. We'll come back to it in a minute. The big thing that everybody wants to know about, though, is discrete GPUs. Can I use them? And the answer to this question is, it's complicated. AMD GPUs just work as long as you have compatible PCI Express implementations. Note that for a moment. Basically, anything GCN 1.2 or later is going to work fine. Older stuff works well also. It uses a different driver. It's fine. NVIDIA is very complicated. We don't have any CUDA at the moment. NVIDIA has said that they are going to bring CUDA to RISC-V, but they're going to only do it for RVA23. The other part of the problem is, depending on which card you have, you either use one of the now 3 open source drivers available from NVIDIA. There's Nouveau, there's the Nova drivers from Intel, and there's the new NVX drivers from NVIDIA, all of which are open source. They all work on different GPUs. It's a nightmare. Oh, and there's firmware. Don't forget about the firmware. And then the last one is Intel Arc. There's bring up happening right now. From what we understand, everything should just work, with the exception of video encoding, but we have a chance of making that work using just-in-time emulator stuff, which is kind of what I'm demoing at the booth, which is neat. Let's talk about PCI Express. PCI Express is a standard. So the Star 5 JH7110 does have PCI Express support, and I typically tell people that it's for networking and storage only. So you can drop in Wi-Fi cards, you can drop in Mellanox NICs, you can drop in NVMe devices, you can drop in SATA controllers. All of that will work just fine. You can drop in LTE and 5G modems, no problem. Same thing with the SpaceMint boards. You can't really plug in a GPU. On the SWIN EIC 7700, so far, everything works from the SOC standpoint. That doesn't mean it works on every board. A great way to describe this is the Star 5 board, which I have at the booth, happy to show you. It's very cute, it's very tiny, it's svelte. It has a little PCI Express slot in it. You're like, oh great, I can plug in a GPU. Your GPU expects to be able to get between 7 and 10 amps of 12-volt power through the PCI Express connector. The input on that board is limited to 5 amps. You're not going to run a GPU. This is the problem with both of the SpaceMint boards that I have, is that they have a full GPU slot, and they say they're for a GPU, but they don't provide nearly enough power to make a GPU boot. Plus, they're limited to 32-bit memory addresses, and it's missing part of bar, and it only has 2, like, it's a whole thing. So it is complicated, unfortunately. But for the good news is, for the newer stuff that we're all really excited about, this PCI Express stuff is just working, and these are the drivers that you can use. So the Radeon and AMD GPU drivers just work. The only thing that is complicated is with GCN2 and later, the graphics cards require floating point in the kernel. This is a relatively new thing, and some of the vendor kernels didn't have the patches for that, but they're very easy to backport. At this point, I think we have backported them to all of the vendor trees, so you don't really have to worry about it, but it was a problem for a short period of time. Nouveau and Nova, like I said, complicated, no CUDA support, depends on RVA23, looking promising. And then the i9-15 and the Z stuff, bring up is happening, things are looking good. I'll have more details for you in January. In terms of GPU software on RISC-V, if you're using a newer discrete GPU, you want the newest Mesa that is supported by your operating system. Why? In Mesa 24.2, they switched from the MC JIT to the ORC JIT in LLVM for doing all sorts of stuff that is required for shader modeling and various other odds and ends. The MC JIT was built specifically for x86-64, and they hacked in some ARM stuff and then went, oh God, this is a nightmare. And then ripped all of that out and created the ORC JIT, and that finally landed in LLVM 18. It now works correctly on x86, on ARM, and on RISC-V, also on Long soon, if any of you care. And then at that point, you're good to go. So as long as you're running Mesa 24.2, which all of the current operating systems are shipping with, it's great. The downside is all of the stuff that has embedded GPUs are using those imagination parts, and they're shipping with a very badly patched binary-only Mesa 22.4. And so the discrete GPUs don't work, so it's kind of an either-or situation rather than being able to like try and make them work at the same time. Other software works on RISC-V. We have 2 working compilers, so the world is our oyster. You can GCC or LLVM to your heart's content. But in all seriousness, like most languages work. The biggest problem is the things that have native dependencies. So JNI components in Java applications, Ruby and Python FFIs that pull in binaries. My least favorite is Ruby gems that pull in an ancient version of Node.js, compile it from source. It just kills me every single time. Yes, and the other thing is a lot of the pre-built binaries assume that the world is x86-64 because we've been living under 30 years of the Intel hegemony. So a lot of times you have to go back and build stuff yourself. But if you're installing packages from your operating system, for the most part, it is just going to work, which is great because those teams have done the work for you. So wrapping up, we're going to have plenty of time for Q&A. The state of the various distributions as it looks right now. So Ubuntu does a really good job of shipping pre-built images on their website for 2004 LTS using RVI20. You can download them from that URL. You flash them onto a SanDisk Ultra SD card, and for the most part, it just works. Frequently, these servers are what they consider server images, which means they didn't bother with any of the drivers or anything for display controllers or GPUs. So you're going to SSH into the box, or you're going to use it through a serial console. Don't expect the graphics output to function. You can download the 2404 LTSs and then do a release upgrade to get them to 2410 or 2504, and I highly recommend that. The 2404 LTS release for RISC-V was bad. The package situation got a lot better in later ones. And like I said, 25 and 10 and later, which comes out in 2 weeks, will require RVA23. And currently the only supported hardware is QEMU. Hopefully that will get better as time goes on. We're expecting RVA23 hardware next year. Fedora on RISC-V. So the Fedora team has been doing an absolutely fantastic job. There is a fork of that team, which is essentially a spin and a SIG based out of China called the Fedora 5 Force. And they make a fantastic thing called images.fedora5force.org. You can download SD cards ready to go for a wide range of RISC-V boards. Drop it in, you're good to go. They have Fedora 41 images, Fedora 42 images. They do the work to make sure that the onboard GPU functions. And it's really easy to turn that off, as I learned today. So if you want to just use the software stuff or use a discrete GPU, Fedora 42 is available now. Fedora 43 is available soon. And like we said earlier, the plan is with Fedora 44, they're going to have an RVA20 and an RVA23 branch. So you can use whichever one is best optimized for your hardware. Debian. Trixie is currently shipping. It has full RISC-V support. It's using RVI20. Everything's spectacular. You can get QEMU images from Debian.org. Installers don't work on most boards, but you can do a DE bootstrap. So the trick that I do to try and get a lot of these things up and running in Debian, I go to the Fedora Force 5 team. I download their image that works on the machine, drop that in, plug in like an NVMe drive, copy over the bootloader partitions, do a DE bootstrap onto it to get Trixie, reboot, the world's your oyster. RVA23 has been talked about with the Debian team. They're not going to switch to it until there's multiple boards supported by vanilla upstream kernels because Debian has standards. Gentoo is interesting, much like Debian, no ready installers. You can get a QEMU image. It's slightly broken. I have a bug open on this. I don't know who to tell to fix it. Basically, they installed the grub package, but didn't do the grub install command. So it can't find grub. It's really easy to log into, like open up 2 QEMUs, log into the machine by mounting the disk image, run the grub install command, and then everything just works. But I'm working on trying to get that fixed upstream. You can DE bootstrap a stage 1 or stage 3 image and get started on your hardware. And because Gen 2 is entirely source-based, you can do fun stuff like set mCPU and mTune to get the maximum performance out of your system as possible. funroop, all of those things, rice your Gen 2. Then we have Arch. Like I said before, first project is being an alternative architecture. That's where you can go get it. They have images for a couple of the JH7110 and Spacetime boards. Really easy to get started with this, and there's a lovely community on Matrix to answer questions if you run into a situation like, why is KDE broken this week? Usually it's because there's a file conflicting between two packages. This brings us to the how can you help section. So I'm going to make a statement as you all are reading this slide that I wanted to talk about, but I didn't want to put in the slide, which is a lot of the stuff that you have to do to get things working on RISC-V is usually very low-hanging fruit. It's just as simple as like add RISC-V 64 as a supported architecture, sometimes update some auto-config pieces. Pretty straightforward, relatively easy. The sort of thing that people go, hey, I can get an agentic coding tool to do this for me. And if you do that, and you are going to contribute back upstream, please include in your contribution which agentic coding tool you used, and look to see if they have a policy of whether or not that is okay in your open source project that you're submitting to, because speaking as an open source maintainer, this is a lot of work, and LLMs are making it worse. But other than that, it's pretty straightforward to get stuff up and running. This leads to the last two things I want to talk about, which is where can I get help? There's a lot. I've started a project to do that. So works with RISC-V.net. We have a discussion board. We have a Discord. I'm working on a forum because the web should be searchable. We have a wiki with info on hardwares and guides on how to get your favorite operating systems working on those boards. We have a blog, and I'm willing to accept contributions from everyone. And the idea is to try to make it web searchable. And as I talked about, we're going to have video content next year. Can we hang out? I organize the Austin RISC-V group. We meet at least once a month. There is a channel for us on the Works with RISC-V Discord. There is the URL because I was tired of spending $300 a year on meetup.com. Can you get hardware? Absolutely. Terms and conditions apply. Really what that means is there is a lot of stuff available for purchase. I'm an early adopter. So basically, if you see something interesting, usually the correct question is, Carl, have you bought this yet, and does it work? I have a few things on pre-order already. I'm that guy. So my goal is to try and get Handworks working on a lot of this stuff so that people can help get things up and running. RISC-V International has a dev board program. So you can make a submission to that dev board program and say, hey, this is a thing I want to do, and they will send you one for free. Resources are limited. There are restrictions, but you can just fill out a form. I'm happy to get you in touch with the right people. Virtual machines, containers, cloud resources are all available if you dislike running hardware. And with that, I think I have like 2 minutes left, and I will take any questions. Yes?
Has anybody tried to do ROCm yet with the NVGPU on RISC-V?
Yes. A lot of ROCm is kind of a mess because basically it is an internal paid development project inside of AMD, and then when they go, great, it's time for a release, the lawyers go, wait a minute, and it spends 3 months being looked at for the lawyers before they can make the open source release. So patches are being submitted back to them to like enable it on other platforms like ARM and RISC-V, but it's a very slow process for them to get rolled in and back out because of the whole legal standpoint. So it's coming, it's just happening slowly. Yes? The future of this is eventually all three. Right now, not. Like, if it's something that you find interesting and you want to play with, it's great. If this tickles your brain in the way that it does mine, like, I'm happy to help you with it. If you just want to sit back and wait until you have something that has UEFI and you just plug in a Ubuntu USB stick and it all just works, we'll probably be there in about 3 to 5 years. You had a question?
Language support, you said GCC, so that's C, C++, Python.
Yep.
You said
Go is good to go. You can actually go download it from golang.org. It is officially built by Google, has been since 1.20. So yeah, basically, like I said, every language is there. Even Haskell, even weird stuff that you haven't thought of, like OCaml. Like it all works. It is not necessarily fast because there's usually a lot of optimizations that go into the x86 and the ARM stuff, and that's not ready yet. As we get RVA23 hardware, those optimizations will come along. It's also a great place if you're like, I'm interested in, like, this particular language speaks to me and I would like to make it faster. Like, let's have a conversation about how we can learn the vector stuff and how you can bring that into that language to make everybody's lives better. Also, there's projects like Rise that will pay you to do that. Yes? If you were fabbing hardware, what's in it for you? You don't have to pay ARM. And that is huge.
You don't have to pay anybody.
Correct. You don't have to pay anybody. You can license cores from companies like Sci5 and Andes and Akeina, and I'm probably missing one, and I'm sorry, whoever's watching this video. But you don't have to. There's a lot of folks that are making their own. There's one of my favorite projects in RISC-V is this thing called the Open Hardware Group. It was a combination of Silicon Labs here in Austin and Thales in France. They were like, we make products. We need processors for these products. We don't care about the IP for it, so we're just going to open source all of it. And all of that is available for everyone to use, and it's great. I am out of time. Thank you all very much. Feel free to come by if you have any questions.